Hello everyone, let's solve a problem from GATE 2021 Aerospace Engineering paper question number 38. The question is to estimate the aerodynamic loads on an aircraft flying at 100 km per hour at standard sea level conditions. A 1/5 scale model is tested in variable density wind tunnel ensuring similarity of inertial and viscous force. The pressure used in the wind tunnel is 10 times the atmospheric pressure. Assuming ideal gas law to hold and the same temperature condition in the model and prototype, the velocity needed in the wind tunnel test section is dash. We have been given four options: 25 km per hour, 50 km per hour, 100 km per hour and 20 km per hour. We have a real condition where the aircraft is flying in the atmospheric condition at 100 km per hour. So we have to test it in a wind tunnel using scaled model. So the scale that we are using is 1/5 of the prototype, and we are ensuring that there is a similarity of inertial and viscous force, which is the Reynolds number similarity. We will equal the Reynolds number for both model and prototype, and also we are assuming that the ideal gas is holding for this condition and the temperature for both the conditions are equal, right? Let's go and solve the problem. Let's first write the what are the variables that are available to us. So first, the velocity of the prototype, which is aircraft is running at 100 km per hour, and the model's velocity is what we have to find, which is um, and then the pressure is atmospheric pressure for prototype, and the model has a pressure 10 times that of the prototype, right? So next one is the length scale. So the length scale of the prototype is LP, and then the length scale of the model is 1/5 of the LP, right? And we have also been given that the temperature for both the conditions are equal, right? So one more condition is that there is a dynamic similarity of inertial and viscous forces, so which is the Reynolds number for both the cases would be equal, right? So Reynolds number for model as well as the prototype is equal. So that is what we are going to equate to solve this problem, which will be rho m um lm by mu m is equal to rho p up lp by up. Okay, so let's so we have to find um, and we know up, and we have a relation for lm and lp as well, and we just have to find a relation for, and we have been told that it's a variable density wind tunnel, right? So the density will be different. We have to find the relations for the density for both prototype and model, and we also have to find the relationship for the viscosity, right? Now let's use this condition. The temperature for both the model and prototype is equal, and we know that the viscosity is a strong function of temperature, and hence since the temperature is same for both the conditions, so the viscosity also will be equal, right? So we have found a relation for this, so this both will be cancelled now, right? So let's find a relation for the density now. So we have a relation for the pressure, right? So, and we have also been told to use the ideal gas law, right? From the ideal gas law we know that the P is equal to rho RT. So if we write it for the prototype, then PP is equal to rho P R into TP, right? So if we repeat that for a model, we will get PM is equal to rho m R TM. So we know that PM is equal to 10 times PP. So let's substitute that. So then we will get 10 times PP is equal to rho m R TM, right? So instead of PP, if we substitute this value, then we will get 10 times rho P R TP is equal to rho m R TM, right? So we know that R is same for both the conditions. It's a universal gas constant, and the temperature is also equal for both conditions. Then RTP, RTM will get cancelled, right? So we cancel that, then we get a relation for density, which is rho m is equal to 10 times rho p. Okay, let's go and substitute these two relations in this Reynolds number similarity. So mu p is equal to mu m, let's cancel that. so we will end up only with the numerator. So let's substitute, instead of rho m, let's substitute 10 times rho p, and instead of Lm, let's substitute 1 by 5 into Lp, right? So now if you see rho p, we have rho p on both sides, let's cancel that, and we also have Lp on both sides, we'll cancel that as well. So then we'll end up with 10 um by 5, which we will get 2 times um and equal to up, right? So 2 times um is equal to 100, which is up, that is the aircraft's velocity, right? So now then the model's velocity will become 50 km per hour. So the velocity required for the wind tunnel is 50 km per hour, which is the option B, which is the right answer. So the NPTEL reference for this particular question is from the course Introduction to Fluid Mechanics by Professor Suman Chakraborty, and the particular video that you want to have a look at is from week 12, lecture number 60, which is Principle of Similarity and Dynamical Analysis, and you can also see the YouTube link for the particular video. That's all for this question. Thank you.